Consider a piece of the curve, and suppose I want to revolve that piece of the curve about the x-axis. What I will generate is not some kind of solid of revolution, but simply a surface of revolution. It's not filled in. It looks somewhat like this. Somewhat like a speaker cone. Now, to compute the surface, or shall I say, to compute the area of the surface of revolution, imagine partitioning an interval from A to B into n subintervals, concentrating ith subinterval, and therefore concentrate on just an ith piece of the surface of revolution. Now, for that one piece, if I bring it over here, and maybe take a piece of paper, since this is just a speaker cone, cutting it, opening up that strip of paper you see in red, I think it's going to look like this. It almost looks like a rectangle. But here's approximating, say, for example, the curve in black over the I sub arrow with a line segment. Notice how this length right here is nothing more than the circumference of the circle. That's computed by looking at 2 times pi times a radius, but the radius is clearly y sub I asterisk. That being the case, I think how we're going to compute the area of the surface of revolution, if it's revolved about the x-axis, we will simply compute the surface area as nothing more than the circumference, 2 times pi times a radius. That y sub I asterisk will become a y once I take the limit of the Riemann sum, and I'll multiply by ds. Now that's if I'm rotating about the x-axis. So keep in mind, this essentially tells you that you have 2 different formulas in your back pocket for computing this area, because it is the case that ds can be computed in 2 different ways. And again, you're going to choose whichever one generates for you an integral that's easier to evaluate. Now, if I choose this version, that factor y will remain a y. If I choose this version where my variable integration is x, I have to convert that to x by looking at the relationship between x and y that describes the original curve.